Alright, so let me just switch the screen and show you the problem. So, second problem of today, I'll be doing 3 problems in total today. CMOTST 2008. Given that ABC is a triangle, and the line L cuts the lines BC, CA, AB, and DE and F respectively, O1, O2, O3 are circumcenters of the 3 triangles. Prove that auto center H of the triangle formed by the circumcenters is on line L. So you might think, first of all, let me just scribble something down. Switch to the iPad. First of all, first question, get it out of the way with first. Okay, wait, let me get my pen. First question I might have, how does a line cut a triangle 3 times? Because they said line L cuts the lines BC, CA, and AB, so it cuts all 3 sides. All 3 sides. Well, the answer is it doesn't really cut all 3 sides, because that would have been impossible. Let's just say you take some random triangle here, A, B, and C. This is not our actual diagram, but if you draw a line L, you realize that every time, at most, you can cut 2 sides, but then the third side is the extended of BC, for example. Then you cut here. So it's not cutting the actual side, but cutting the extension of the side. So that's the first thing out of the way. Next thing, let's get into the actual question. So basically we have to draw a diagram, and let me outline how we're gonna do this. First of all, okay, let's write transport actual solve. Basically we need to prove that let's remind ourselves, prove that orthocenter H of O1, O2, O3 lies on L. And first of all, let's draw the diagram. So we have should I draw bigger? Fine, I'll draw bigger. Let me draw it down a bit more. Okay, so this is A. Let's draw C somewhere here. And okay, just treat it as straight, okay? BC. Let's say the line cuts like this. So this is D, this is cuts AC at E, this one's F. Okay. So now we're gonna draw circumcircles of AFE and CDE. But first of all, let's mark out the circumcenters. So this one goes something like this. Wait, it's not very perpendicular though. Something like this would do. Yeah. So O1 is here. We just found O1. AFE is BFD. CDE is O3, right? CDE is O3, yes. So let's find this. O3. Now let's draw a circle surrounding this thing. Probably not the best circle, but whatever. Let's try to draw a nicer one. Use this tool maybe. And I can just shift this around. Ah, this is so good. Okay, then too bad in the actual SMO I cannot use this. Just okay, nice, more or less accurate. Then we shall mark this point as M. So ME is this vertical axis. ME vertical axis. Vertical axis. Sorry. Radical. It's too late at night, bro. Still need one problem more to be solved. Okay. Let's just draw some arbitrary lines. MD, MF. ME. Okay, now hopefully the ideal one, this scenario is we want to find out that this is also cyclic. Why? Well, once we know it's cyclic, there's a lot of nice things that we can do with segments and stuff. So we find that it's cyclic first. It's gonna prove useful later. So if cyclic, then angle B, let's just say FBC, so this one, plus angle FMD equals 180 degrees because of opposite segments. Let's just store this in our head, try to prove this. So first we do angle B, which is also angle FBC, is the same thing, plus angle FMD. We can't conclude that's 180 because we don't know. We try to prove that it's 180. Equals, okay, we can split FMD into two parts, right? So FMD is composed of angle FME plus angle EMD. So literally I'm just splitting this chunk into, this chunk plus this chunk plus this chunk. So just splitting it, and FME, okay, FME is what? FME, right, is this one, because of the cyclic quad, it's also equals to angle FAC, which is just called angle A, because this is angle A. For EMD is a bit different. EMD is this, right? EMD is 180 degrees minus opposite, cyclic chord property. So EMD is 180 degrees minus the opposite angle, which is ECD. What is this also? Just 180 degrees minus this one also gives you this, which is angle C. So we got angle B plus angle A plus angle C. What is this equals to? This is literally the three corners of triangle. Sum them up, it's 180 degrees. So we just proved this one. We just proved it, yeah. So now that you know that, let's just write it down. B, D, M, F is cyclic. Now that you know that it's cyclic, you can add one more circle to the gang. Holy shit, this is horrible. I didn't even think I was trying to draw a circle, bro. But that is good enough, I think. Okay. Now we still have to prove that. Okay, let's just draw the third one, third circumcenter. Don't know why so far we left it out. I think somewhere here, which is O2. So basically, right now we will try to prove that. Sorry, this O1, O2, O3 is similar to ABC. So I'm talking about triangle here. Okay. And now note that MF is radical axis between circle with O1 and circle with O2 as centers. So O2, okay, let's try to think. So you can say that MF is perpendicular to O1, O2, and ME is perpendicular to O2, O3. I mean O1, O3. Sorry. So what I'm saying is this line is perpendicular to this line, and this line is perpendicular to this line by definition of radical axis. Okay, so let's knock it out. And this tells me that angle O1 is equals to angle M. Angle O1 equals angle M. And let's see, O1 is equals to M, which is also equals to A because of the cyclic chord. So O1 equals to M equals to A because of the cyclic chord. Yeah. Now can you say bisimilarity? Let's see. Okay, so you can just say by similarity. By similarity, angle O2 equals angle B. Hence, triangle O1, O2, O3 is like similar to triangle ABC. So now that we proved that the two triangles are similar, we can't forget about original problem, proving that orthocenter of this. So we haven't drawn the orthocenter of O1, O2, O3. Orthocenter should be here and it's on L. So let's name it H. So we want to prove that H is on L, line L. So now I think we need a separate diagram. And I'll show you the diagram here. I'm just gonna take this from the answer sheet that I have. Okay. Let me just try to snip the diagram and send it over. Wait, sorry. Sending it over to my iPad. Alright, so I have it open now. Basically, this is like that. Okay, yeah. So we know that O1, O2, O3, O1, O2, O3 triangle is similar to ABC, triangle ABC. So from, you can see from O2, we introduce perpendicular to O1, O3, and it cuts line L at H here. So if you connect, you draw these lines here and here. So you know that O1 is circumcenter of this triangle, and hence O1, okay, this angle by definition is 90 degrees minus angle A. So you write it down, angle O1 FH 90 degrees minus angle A. Okay, and on the other hand, you can look at the other circumcenter, which is this one, O2. If you look at O2 from the POV of O2, what you have is this angle, HO2 and O1, it is equals to 90 degrees minus this angle. So the reason is, if you consider this triangle, you can see that angle H02 O1 plus angle O1 O2 plus this angle, which is 90 degrees, equals 180. So if you minus 90 from both sides, you get angle H02 O1, and you move this over, it's 90 degrees minus angle H01 O2. So, well, not H01 O2, it's O3 O1 O2. Sorry, O3 O1 O2. So angle O3 O1 O2. Yeah, because H is here, sorry, I messed it up. And what is this? Since we have this, so from here, angle O3 O1 O2 equals angle A. You sub A into here, equals 90 degrees minus angle A. So what we have now is that this angle is equal to this angle. This means, oopsies, that you got a cyclic quad. I don't know how you would want to draw this. This is like the hardest cyclic quad to draw, but basically you have something like this. FO2H01 is cyclic due to this being equals to this. So basically this equal to this means that's cyclic. Okay. Therefore, knowing that it's cyclic, let's see, what can you do with, oh yeah, I even draw this circle wrong. I need to include this. Okay, yeah. So this means also I can apply the property to another pair of angles, which is this versus this. So angle O2 FH equals to angle O2 O1 H. So O2 FH, right, is this angle, which is also if you take a look from the POV of triangle BFD, it's also this angle, which by definition is 90 degrees minus angle B. So what else do we know? We know this is 90 degrees minus A. angle A. So what we have here is angle A is equals angle B. No, this is not what we want. This is also 90 degrees minus angle B is O2, right? Angle O1, O2, O3. So angle H O2 O1 plus angle O1 O2 O3 is 90 degrees using this and this combined. You know what that means? Angle H O2 O1. So angle H HO2O1 plus angle O1 O2 O3, right? Angle O1 O2 O3. Wait, I think I messed it up. Angle H O1. Oh yeah, wait, careless mistake. H01 O2. So angle H O1 O2 plus angle O1 O2 O3 H01. So this and this is 90 degrees. That means this angle left is 90 degrees. Okay, that means O1H is perpendicular to O2O3. So that means H is already the intersection between two altitudes. So H is orthocenter. Why is this significant? Because at the start we already assumed H is on line L. So you combine this with the fact that H was on L. That means orthocenter is on L, which was what we wanted to prove. And yeah, that's all.